high, it goes through the blood vessels itself and goes all the way to this location called the left ventricle. Okay, in the left ventricle you can see this pigtail like thing, and then here the blood is entering through the suction there and then getting completely ejected into, look at this location where it is getting ejected. Somebody who is prone to high blood pressure and things like that, and prone to diabetes, or all kinds of additional issues and complications, they do not want to load the heart at that time additionally to do this pumping action. So this kind of a pump, which is used only for 5-6 hours, costs about 20 lakhs. Okay, it's a use and throw, by the way. So the question is, it looks like a simple-minded tube where you can see these kind of suction holes here, and it passes through the hose pipe like this, and then essentially getting ejected here. There are blades there which are rotating. It's more of an axial flow pump essentially. So designing these kind of pumps is something called, it's percutaneous, because you put a hole through the heart and then through the femoral artery and go all the way to the actual location to sort of insert this. I'm sure it's quite worrisome if somebody has to put a stent. The stent operation, etc., may not cost more than 2 to 3 lakhs, wherein the surgeon will be also doing that using, again, essentially reaching the locations of the plaque and then putting a stent there. Again, endovascular, meaning anything where the surgeon need not open something, okay, and they essentially go through the tubes which are already existing and reach the actual location, and where it is blocked, they put a some kind of slightly small opening there, and then essentially put some ballpoint pens have springs, right? That kind of a spring is what they release. If they release a ballpoint like spring, ballpoint pens have springs, right? That kind of a spring is nothing but a stent. Let us see, some of the costs associated with, for example, if the valves are not functional, you require valve replacement surgery. There are at least 4 valves in the heart. So between the right atrium and right ventricle, between the right ventricle and pulmonary artery, similarly between the right atrium and left atrium, left ventricle, and between left ventricle and aorta. Okay, so the names are not important because I do not want to sort of really put pressure by saying names, etc. But think of the following: there are 4 chambers in the heart. Let me see if I have a picture. Here I can see there are 4 chambers of the heart. This is one valve. This is another valve, and right ventricle, you can see that supplies blood through this pulmonary artery to the lungs, gets oxygenated, comes back through these pulmonary veins, and then accumulates in left atrium. From the left atrium, it is kind of fills the left ventricle, gets highly pressurized, high pressure, because it has to go to the whole human body. Okay, not just to the brain and then kidneys and so on, but to the whole human body. Each time, each heartbeat will fill about will eject about 70 ml of blood. Okay, if it is 70 ml per beat, about 72 beats per minute will be about 5 liters per minute. It will be pushing about 5 liters per minute of blood by working 72 times in a minute, essentially. And please notice the valves are opening and closing almost how many 1 lakh times in a day. Am I right about the calculations? You can check. Okay, so 72 24 hours multiplied by 60 minutes an hour multiplied by 72 times in a minute. Okay, that many times valves are opening, closing, opening, closing. Think of the fatigue life of these valves. Valves have several issues. For example, if they're not closing properly, there will be leakages. Leakages are called regurgitation. And maybe sometimes the way in which they're supposed to open and close, open and close, they're not able to open fully, close fully. There are issues of that nature. Under such circumstances, you require valve replacement. Okay. You also need, you will come across several issues. For example, some of these tubes are blocked, some of these tubes are, not, they have bulges or expansions. Some of these tubes have essentially due to, it could be due to genetics, it could be due to, lifestyle related issues where plaques are formed. Think of cholesterol. I'm sure all of you know cholesterol, high cholesterol, low cholesterol, these kind of things. And then, surely LDL is responsible for this kind of plaque formation. Plaques will essentially cause constrictions, meaning essentially narrow the cross-section area available for the blood to pass through. Okay. Here what is shown is as if, you can see three circulation loops wherein the heart from the left ventricle, it is ejecting into the aorta, and that is supplying blood to the whole human body and coming back. That is what is called a systemic circulation, this circulation loop. Okay. And oxygen rich is going, carbon dioxide rich is coming back. Once it comes back to right ventricle, and of course parallelly getting ejected. So from the right ventricle, it gets ejected into the through the pulmonic valve and goes to pulmonary arteries, gets oxygenated in the lungs. You can see this kind of a circuit. Pulmonary arteries, it is going through that, goes to lungs, gets oxygenated, comes back to left atrium here. So the details are not important. Two aspects. Number one, if the heart is non-functional, you require some kind of a mechanical device which can do this pumping action. Okay. What is a pump and what kind of a, the one that I have shown you is not the real heart pump. It's actually a temporary heart pump for about 5 to 6 hours, where the surgeon is working on the beating heart. The beating heart will not have that much pressure in terms of its functional capacity, provided additionally another pump is doing that job. It's like, when you have high fever, think of somebody doing your work in office, taking your classes, doing your research and so on. Something like that. So if somebody taking care of your classes when you are not well, something like that, if that is happening, you will be very happy. You will recover faster and you will naturally reduce it. But if you have to also do the classes, go to, do all kinds of things, additionally go to market and bring all kinds of things with all your fever and so on, surely you are working harder than your recovery time will be, can have serious repercussions. So coming back, some of the costs shown are, related to stent placement, and then there are also flow diverters. I will come back and say this. LVAD operation, by the way, totally left ventricular assist device. Something this costs LVAD pump. I'll show you a LVAD pump. It costs about 1 crore straight. Okay, MGM charges straight away 1 to 1.5 crore. I mean, people can afford, but then the question is, are there cheaper options possible? Are there better options in terms of reduction of the costs and so on? By the way, these numbers are just to attract outside people for medical tourism purpose. They may be attractively positioned. Don't be fooled by these numbers. Okay, these numbers are like you have the lowest possible rate kind of a thing. Once they come, then the medical tourism fellows, they will know what kind of charges to make and so on. So the role of mechanical engineers, where is it coming? Okay, let me straight away go to the story. So one of the early valves that was designed with this cage and ball valve, wherein the suture ring that you see here, okay, that suture ring is essentially stitched by replacing this entire thing. This valve is non-functional, let us say. That valve is removed and a ball and a cage valve is put. So the suture ring comes exactly at this location. Essentially under high pressure, ball will go up, do the thing, but it will not get into the bloodstream. Okay, and there is opening around the ball. Okay, so once there is opening around the ball, and then the fluid will eject. Under low pressure, of course, the ball will fall down. So the ball, spherical ball, is essentially inside a cage. You can think of you just to do some kind of a high pressure, it gets lifted up, low pressure, and naturally, it will come and fall down. Okay. So please notice people have designed also some kind of mechanical leaflet valves called single leaflet valve. So think of a disc opening, closing, opening, closing. Around that suture ring, it will just close like a disc. So this kind of a single disc is also called mono leaflet tilting disc valve. This is something that India also has designed. Please notice for designing this and making it successful, it took about you know two plus 2.5 decades of entire effort by an institute called Sri Chitra Tirunal Institute of Medical Science. I'll show you some pictures on that. So Chitra valve is one of the India's competition to the world. Surely it's doing well in African and Asian markets. It's marketed by TTK Group. And the bi-leaflet valves, they're quite famous, quite popular. And the suture ring is actually, going to be, there will be two leaflets. There will be opening, closing, opening, closing. The question is, they will not be opening and closing on their own. Under high pressure, when the ventricular ventricles contract, they open. The ventricles relax, they just close. Think of two half circles, opening, closing. So these are called mechanical valves. You can see the hinges here, hinge design, the leaflet design, how the flange should be designed, and then there are many aspects. One could be thought in terms of under slightly higher pressure how it should open, and under slightly lower pressure how it should close. That must be naturally happening over a much longer time frame. If the valves are designed for about, let us say, 20-30 years, and it has to last 20-30 years of lifetime, so that many times of opening and closing, we are talking about a high cycle fatigue issue. And of course, the key concerns will be, it has to be, first of all, passing through the design stages. It has to be experimentally proven outside. Then you have to implant it to animal experiments wherein, it's called preclinical. And they will put inside an animal, and then animal has to sort of survive for a certain period with a mechanical valve like this. And then I'm very sure, conducting animal experiments and showing the success of those animal experiments, maybe the human trials will be allowed. And there are many stages associated with such valve development. It's very important that mechanical engineers sort of get involved as stage one, some kind of CFD based designs. You can see here there is a mechanical arc valve which is implanted, and the suture ring is actually what is sort of stitched around that. Older one is removed totally. You can see this old one is removed totally, and then the mechanical valve is put in. Once a mechanical valve is put in, there could be certain number of years of guarantee done by the surgeon and so on. But then again, naturally you want this valve to function and do a good job. Then comes the different types of other valves. These are called they're called bovine valves, essentially tissue valves, bovine or porcine kind of valves, where from the about I think 8 to 9 month old cows, they're specially sort of only bred for this kind of purpose, and these kind of valves are developed, and then there is a very elaborate process by which these um, tissue valves are generated, meaning tissue valves again could be also supported by some kind of transcutaneous rings and so on. Let us see some, some of these valves which are having names again, because the whole purpose is not really. I was mentioning about stent, and you can see the plaque here. Plaque is essentially cholesterol deposition, and you will be, by placing a stent, you will be pushing the plaque slightly outer, in the outer direction, in the radially outward direction. But a structural integrity associated with that cross section area is now made available. If this stent is not placed, this plaque will keep on growing. Of course, it grows underneath the endothelial cell lining. The cross section area here, you can see it will continuously decrease if stent is not there. And in turn, this entire tube, which is supplying blood to the distal side, to the downstream side, may completely get blocked. I'm very sure. I mean, this is very, simple-minded thing nowadays for people. This is about IABP, intra-aortic balloon pump. Essentially, a balloon-like thing is used. On top of that, a stent will be located and placed. Although this picture is showing slightly as if plaque is removed, plaque is essentially pushed outwards, radially outwards. Okay. The pump that I was mentioning is a VAD pump, left ventricular assist device, which looks more like this, an axial flow pump. It's very different from the Impella device that we have seen before. Impella is a temporary pump, whereas this pump is meant for about 15-20 years of working, or even longer. And this operation is what I was saying costs about 1 crore, or 1 crore plus essentially. And designing such pumps, also requires a lot of collaborative effort between cardiovascular surgeons, and then recently Madhusudan Sai, the Sat Sai Baba's, he has recently sort of supported some huge amount for Impella pump. And I'm just showing you the pictorial drawing. You can see from the left ventricle, blood is you can see the blood is drawn, and it's pressurized and put back into aorta. This inverted U tube that you see is called aorta, and the pump will be working on the batteries. Okay, the batteries are here. You can see the batteries, and the entire controller unit is outside. This entire pump is along with closer to the heart. It's inside the chest cavity. And this part is completely, I mean, there are issues like if you put a cannula like this, you put a suturing of that, there is a possibility of blood leakage around this. And then, there are issues of very serious nature. And when you essentially pressurize the fluid, in the process, the Impella, or in this case, the axial flow pump has blades, which are likely to be slightly pressurizing, and in the process, high shear stresses are generated. If the shear stress is very high, red blood cells can get damaged. You can see some of the early patients enjoying, this guy is having a mechanical heart. His actual heart is non-functional. This left ventricle, right ventricle is unable to do the pumping action, meaning it's not able to generate contraction, relaxation. Contraction, relaxation. That kind of a contraction, relaxation, even if it is doing, could be doing at a very low ejection fraction. It's very important for us to understand how the heart itself works. Think of this more like this. You have a chamber which will fill about 140 ml, eject by contraction into aorta about 70 ml every heartbeat. Okay, that sort of a pumping action is something quite serious, and then designing such pumps is the role of mechanical engineers is very high. Surely it's this guy, you can see this, he's going with batteries, and then he's looking very normal, but in fact his heart is a completely mechanical heart. So the question, India has developed this Chitra valve, by the way, and recently Professor Valli Attan passed away, and Professor Valli Attan was, the story is that Professor Valli Attan was specially invited by Mrs. Indira Gandhi to start the institute, and this is the only DST institution which is medical science related. So it is supported by Department of Science and Technology, called Sri Chitra Tirunal Institute of Medical Science and Technology. This is in Trivandrum. And of course, we're talking about the development of Chitra valve, which under his visionary leadership, this was done, like by mid 90s, this was available. Somewhere around the late 70s onwards, they were working hard on the structural integrity of this kind of a tilting disc valve. And then some of the failures were related to the welding associated with these, you can see at this location, there were some welding failures. Then when the valves are opening and closing, are they resulting in cavitation and then, they're generating bubbles, cavitating bubbles. Cavitating bubbles can be quite dangerous if they explode. Okay. So very important that the rates at which the tilting disc valve is opening, closing, and acceleration, deceleration associated with that. And then hemodynamic design is central. And then again, structural integrity with silent operation and complete absence of cavitation. These are all issues of interest. By designing a simple-minded, we're talking about a valve design. Okay. It may look like very simple valve design, but it has to function inside the body. 72 times it has to open and close in a minute, and think of that in terms of its lifespan. Okay. So I think I do not want to bore you with this kind of details, how the electrical activity is responsible for mechanical activity generation. I'm sure in movies, all of you would have seen this kind of a P-wave, QRS complex and a T-wave. There is a connection between the electrical activity of the heart and the corresponding mechanical activity of the heart pump. Even prior to this, how electricity or bioelectricity is generated in the heart is essentially based on the cellular activity. We'll not go into that. There is a chemical cellular activity which results in electrical action. Only thing I'm concerned as a mechanical engineer, if I switch on the light, okay, my fan starts working. Okay, that's how I will look at it. Okay, if there is an electrical circuit problem, okay, electrophysiologist will come into picture. We can also explain this, but then that will digress. There is also heart valves open and close. When they close, lub-dub kind of sounds is what we are referring. Let us look at this. The two atria will supply, sort of fill the chamber, left and right ventricle, left ventricle. And by the way, the one that you see on the right is always left ventricle. This is called left ventricle. Okay. The one that you see on your left will be right ventricle. Please remember, it is always that of the patient. Okay. Not what is left and right for you. Okay. So this is how it goes, and then I think I'll skip this ventricular diagram because it. Let us look at how the ventricles fill. This is very important because we, as mechanical engineers, are familiar with PV diagrams and then also TS diagrams. PV stands for pressure volume. Okay, TS is temperature and entropy. This is something that you will be teaching in engines, right? Extensively for cycles, thermodynamic cycles, starting from ideal cycles all the way to real cycles and so on. Here also the same thing essentially. You have the left ventricle, I'm just giving as a reference, pressure on the y-axis, volume on x-axis. I'm filling the left ventricle. Essentially, left ventricle is relaxed and sort of it is expanding because it's filling. Okay, that filling process, initially there is about 65 ml inside already. It fills all the way to 135 ml, about 140 ml almost. Okay, so at that time, all the valves will be closed, and then there will be, isovolumic contraction phase. This point B is called end diastolic volume, meaning the relaxed filling is complete. Now all valves are closed. because all valves are closed, you can increase the pressure by readjustment essentially. So the pressure is increased. This process is called isovolumic contraction. So the once contraction is complete, there will be pressure, very high pressure is generated. You can see that about 80 or 90 mm of Hg pressure is generated in the left ventricle. It keeps on rising because it's pressing harder and harder as it is contracting against pressure. So it ejects into the aorta, the largest tube in the body which supplies blood to the whole human body essentially. And there is a gradual, you can see that at this point, about 70 ml of blood is ejected. So there is an isovolumic relaxation. This kind of contraction resulting in blood ejection is called isovolumic. Sorry, you can call it under constant pressure, but typically it doesn't happen at constant pressure. Because the fluid is trying to sort of get pushed outside, pressure keeps on increasing. The left ventricle also keeps on increasing its pressure up to some point, and beyond that it starts decreasing. You can see this is what you call as systemic, this is related to the systolic part, where systolic contraction happens, diastolic relaxed filling happens. So you can see a nice PV diagram here. So then the question comes, what is the work done by the heart? You can integrate the PV diagram and get it, and so on. And this is what is called stroke volume. In one ejection cycle, 70 ml is ejected. If there are 72 such beats 70 times, you can see 135 minus 65 is approximately 70 ml is what is typically happening for a normal heart. Please notice I am identifying two things: stroke volume. If the stroke volume is about 70 ml, excellent. The actual fill volume is about 135 ml. Okay, about 135 is filled, about 70 ml is pushed out. So remaining 65 is left out. Okay, so your 70 divided by 140 is what is called ejection fraction. How much of blood is ejected from the left ventricle in each contraction cycle. If 70 ml out of 140 ml filling is ejected, 70 by 140. Therefore, ejection fraction is 50%. Excellent heart condition. Most of us will have 50 to 60%, 65%, and so on. The heart rate multiplied by your stroke volume is what is called cardiac output in a minute. How much of blood is getting pumped by the heart is what is called cardiac output. And of course, it's also depending on the size of the body, therefore body surface area is important. Cardiac output divided by body surface area is what is called cardiac index. One can also see what is the left atrial pressure, wherein from the lungs it's coming back at certain pressure. So if the left atrial pressure is the place where before it goes to the it's coming back at this pressure before it goes to the right ventricle. So left atrial pressure and mean aortic pressure, the difference between these two is what maximum minus minimum. You can think of this more like a delta P. And the stroke work is like, stroke volume multiplied by your per delta P essentially. Delta P times volume is what you are looking at as your work done. So the key questions, before I jump further, any questions, concerns, and how we are doing on the time, and then let me sort of see if there are any questions online or any concerns. Any questions? Anything that you guys want to ask? Because it is also a slightly different area, so I do not want to rush and brush the things and then. So let us see. Any questions? You can open or towards the end, Dr. Lalita Narayana ji. Is it towards the end, or we can also ask in between?
So end of the session, sir.
Okay, end of the session. End of the session is a little scary because it's like whole 1 hour, 1.5 hours after that I ask them to ask questions. Then They may not. They may feel, oh my God, I wanted to ask that question. I So let us see what problems of fluid mechanics interest are essentially there. I think some of these are research questions. You do not worry too much. Whether an axial flow pump is better or a centrifugal pump is better. How to improve, the cardiovascular health by improving the cardiac output during exercise. Can we tell a patient with a, let us say, with a stent to do some light exercises? If so, how to increase the level of the exercises? 1 week later, 10 days later, 1 month later, 1 year later, how we can do all simulations. That's the beauty of simulations. Without really taking risk, we can do simulations. And I want to introduce two words here. One is hemolysis. Hemolysis is simply, the lysis, essentially red blood cells are present. There are millions and billions of red blood cells in a 1 ml of blood. And red blood cell is like a small 6 to 8 micrometer in diameter and about 2 mm in thickness. It's a semi-discoid kind of a shape. So that kind of a red blood cell can get completely broken. If it is broken, hemoglobin comes out of it, and that is what is called lysis, killing the red blood cell, and hemo comes out of it, and therefore red blood cell death is some kind of hemolysis. This is dangerous. If you kill in the process of blades rotating, if they kill a lot of red blood cells under high shear stresses, okay, you are only damaging the blood. You are not helping the blood. Blood is active fluid, by the way. It's all live, live fluid. Then come to thrombosis. Thrombosis is about clots are formed. I can show some clots, but then the clots are more like wherever there is a bit of problem, platelets will go and do the repair, and they want to help you essentially. And in the process, clots are formed. Clots are good, but if the clots are dangerous, if it is formed inside their blood vessels, because these clots can dislodge, they can get removed slightly under high pressure, and they can go and become some kind of a emboli. Emboli is essentially a block. If there is a block inside the brain, that can result in again another type of stroke. Okay. Again, I do not want to really cover too many things, but how design cycles actually work, let us see. So to start with, you have design cycle. You can do CFD, computational fluid dynamics, conduct some in vitro experiments in the laboratories, see whether the valves are opening or closing or not, and do some mock circulation loops, and see under similar pressure ranges are they opening, closing. Then of course one can do pulse duplicator kind of experiments and so on. The real heart itself is kind of simulated as if where you can see through and then do particle image velocimetry by sending laser beams and things like that. And many types of experimental concerns can be addressed by doing laboratory experiments plus CFD. CFD, you are not killing anybody, so therefore it's much easier. But relevance of CFD also need to be proven, and then large scale CFD has kind of extensively helped, because what a surgeon cannot measure nowadays, CFD can give you some. Of course, the simulations have to be really accurate, and computational fluid dynamics algorithms have to be really powerful. Only then you can think of doing a good quality CFD based design. Then optimizing the designs, etc., is possible using CFD. I do not just mean CFD. It also includes fluid structure interaction, and then where the ventricles contracting, relaxing, all that is kind of indirectly taken care in your fluid structure interaction simulations. And you also answer a lot of what if type of questions, and then mathematical model needs to be built. To what extent your mathematical model represents the reality or not. Yes, somebody has a question. So then we can result in some kind of optimal designs. Then you are really comfortable. Then do preclinical. Preclinical is called animal experiments. I mean, they also sacrifice. They'll implant in a pig, and they will implant in a, uh, you know, 8 or 9 month old bovine. Bovine essentially, bovine means cow related, and porcine refers to pig related. And they do bovine and porcine and even canine experiments on dogs and things like that, because they are the closest in terms of our, uh, mammalian species. And then people can go for human trials. Of course, there are many stages. CDSCO is what is the standard. FDA, Food and Drug Authority, is the standard in US. The final approvals, etc. Again, we are referring to several stages passing. Yes, please. Somebody has a question. Passing all those stages are very important. Here, I'm going to briefly talk about what kind of steps are required in CFD. The vascular disorder, or let us say valve is not working and therefore you want to replace a valve or put a stent. How much of blockage is okay? 50% blockage is okay, or 70% is okay. Beyond 70%, what happens? Beyond 90%, what happens? We can do simulations and then say that no, if the pressure drop before the blockage and after the blockage is by this much, something called fractional flow reserves. People compute FFRs and then say that no, stent is required now. Okay, and of course, identification of a good quality mathematical model is central for CFD. All that may be available in some kind of a commercial solver, for example. Fluent, a very general purpose CFD solvers are available. And even open foam is now extensively used, for example, in our group. And we also need to write a lot of user defined functions additionally. Then patient specific vasculature is very important. Get the anatomical structure of that patient to the realistic conditions by doing the images. I'll show you some pictures. And of course solve the PDE with patient specific boundary conditions. The volume flow rate of that patient through that artery is very important. And then of course, so this is about mesh generation. You do a mesh generator and then solve the equations. Of course, iteratively you solve the equations. And once you solve the equations, you do post processing. Whatever are the questions of interest for you, you will be addressing those questions. You will say, no, I want answer for this question, this question, this question. How much of blood supply after bypass goes to brachiocephalic artery, let us say, after putting a certain type of bypass. If I have put a bypass by, a bypass surgery is essentially leaving a part of the plaqued region and connecting another tube from the upstream to the downstream, so that downstream blood supply is restored. And in the process of doing that, what are the advantages and what should be the size of the tube, what should be the size of the connections, what should be the angle. All that can be done through something called virtual surgeries. This is exactly a cardiovascular surgeon or a cardiothoracic surgeon or a neurosurgeon is actually looking forward to. So they want clinical decision support from engineers. Mechanical engineers are the right people to help them. I'll introduce one class of diseases called cerebrovascular diseases. I think this is about blood supply to the brain. I'm sure all of you know about stroke. Stroke can be of two types. One is where you can see this here. A blood vessel is ruptured, therefore blood leaks. Okay, this is quite dangerous, and suddenly the person, it's an emergency for sure. Blood is leaking inside the brain because the blood. You think of the following: you are getting water supply through several pipelines in your house. Suddenly, a pipe is bursting inside your home or something like that. Then I'm sure that's a dangerous or serious situation because blood vessel is bursting here. It depends on the size of the vessel, whether there is space there or not. After that, what exactly happens? The person gets into some kind of a sudden fall, and then how quickly the person needs to be sort of helped in terms of this is called hemorrhagic stroke. Hemorrhage is essentially referring to blood leakage. Please notice a vessel or a tube has ruptured, blood is leaking, serious, inside the brain. Okay. Then you have a clot or a thrombus here. Thrombus is essentially a clot. Clot is not allowing this part of the vasculature or the blood supply tubes to get oxygen supply and nutrient supply. Therefore, this part of the brain tissue completely is deprived of oxygen. If a part of the brain tissue is deprived of oxygen, naturally, that part of the brain tissue will die. The maximum will be like 5 to 6 minutes. If the part of the brain tissue is dying, recovering it back will not be easy sometimes. So if this clot can be removed using clot retrievers, if the clot is in a slightly bigger vessel, okay, they will send the clot retrievers, hold the clot, and then bring it back nicely. Okay, but such clot retrievers need to be designed. How to hold the clot as you are poking into the clot. Clot should not go and block the smaller tubes. While poking the clot, you should not be sort of rupturing the blood vessels also. Quite serious. The way in which it is done is like some kind of a flower-like thing is opened on the back side, on the front side, and both of them will be holding like this, and they will bring the outside very carefully. But it's not possible to use clot retrievers everywhere. In large vessels, it's possible. But again, this type of stroke is simply called ischemic stroke. Of course, stroke I'm talking about. The face is falling down on one side, other side of the face is fine. There is arm weakness on one side, other side is perfectly fine. There is a slurred speech. Speech is not incoherent. Speech becomes incoherent, and the person has difficulty in speaking, and then they call. There's time to call ambulance kind of thing. So the person has just suffered with paralysis stroke, meaning if the left side is having some problem, right side there is some clot or something. Therefore, this person has difficulty. The right side of the brain controls the left side controls the right side. Of course, the functioning of the brain is another big full-scale lecture. I don't want to get into that. But the key part of it is something called, you can see the blood vessels here. This is more like a ring. Okay, this ring is called circle of Willis. And the circle of Willis will be essentially, you can see, the heart had 3 pipelines. You can see this. So this kind of what should I say, brachiocephalic essentially sort of moves into subclavian, and then additionally this is some kind of a right carotid, common carotid artery, right side. And then you have the left carotid artery, and then all of these are one of the most essential tubes supplying blood to the head, neck, arms, and so on. And as you go down, of course, the story becomes the concern here is about blood supply to the brain. What exactly happens, and then what kind of work we have done. I want to come there. You can see some of these. Bulges are called aneurysms. This kind of circular structure is called circle of Willis. You can see the 2 vertebral arteries are joining to form the basilar artery. And as the fluid is passing vertically like this, in fact, it's not vertical, it's, it could be even horizontal, depends on the anatomy. There is a possibility of bulge for some people. Why aneurysms like this? Aneurysms are essentially bulges, expansions. Okay. Why a certain type of aneurysm is formed, etc., could have several, pathobiology issues which we are not interested. Once an aneurysm is formed, how to treat it and how mechanical engineers can help. For example, you can see the plaque here. Once you see a plaque which is reducing the cross-section area of this tube, this is some kind of middle cerebral artery, wherein the cross-section area has reduced drastically, and then they will release a stent there, meaning to make sure there is sufficient cross-section area available for the blood flow to take place. The entire circular ring-shaped plaque is not gradually narrowing to become, the flow passage. You think of the following. If the cross-section area reduces by half, remember velocity doubles. If the velocity doubles, I'm talking about average velocity. Okay. If the cross-section area is half, average velocity will become double. If the velocity is double, gradient of velocity called the wall shear stress will shoot up. If the wall shear stress shoots up, it's like, a normal road, high-speed race vehicles are moving. Like that, blood will be going past that cross-section because mass is conserved. If mass is to be conserved naturally at very high speed through a small narrow cross-section, it will be squirting through. If it is squirting through a small cross-section area, it will damage the inner lining of the blood vessel. So the inner lining is something called the endothelial cell lining. Once it is damaged, it's going to result in serious consequences. But of course, that's related to pathobiology. Let us go to the specifics. We are talking about doing CT angio. People will go through, computed tomography, angiography kind of thing, and then so that you can see the blood vessel is having a bulge here, and such bulges are not uncommon. You can see the bulge here, and this is an operative picture, and surgeon will have several options. Okay, so I'm talking about this kind of a bulge aneurysm here, and the surgeon will essentially open the skull and put a clip there. I'll show you what kind of clips, Yasser clips, etc., were designed originally, and I'll show you what kind of solutions are possible if they find an aneurysm or a bulge like this. Okay. Now it is also done endovascular, meaning they put a hole in the thigh, through the femoral artery. They go all the way to this location and fill a coil there. How a coil looks, how to design a coil. Yeah, here I'm, again talking about the same thing. You can see this normal blood vessel branching into two vessels, and you can see an aneurysm or a bulge there. Bulge has ruptured, and there could be sidewall aneurysms. There could be, scenarios where, you can also think in terms of, I think this is a nice video which I generally like playing. This is this lady by name Emilia Clark.
Don't call to PSN.
Sure, all of you will know.
PSN guys are calling, I think so. Continuously to Francis sir. Why? Sir has informed to Sir said, inform to Sanju sir, don't call to PSN. Sir, voice nothing.
This is an old story, of course. Emilia Clarke had aneurysms, and naturally, of course, she's back to normal now. So we are referring to these kind of bulges in the blood supply to the brain, and what exactly a surgeon does. I mean, here I'm giving some examples of Sarvanan's actual thing. You can see what they do. They try to sort of, there could be blood vessel rupture, and then suddenly blood will ooze out. But once they open the skull, they know how to sort of look at the kind of speed at which the blood is oozing out. Very, very scary experience for a fellow who is just watching a video. Then think of the real conditions that they essentially do. So role of neurosurgeon. Okay, neurosurgeons will be sort of when there is a blood leakage like this, For geriatric patients, old patients, they will essentially do some kind of partial coiling, something like this, so that they're ready for some kind of a stent-assisted, condition, and then they will put a stent and they will complete coiling is what they do. I mean, these are all endovascular, meaning the skull of the individual is not opened. It is just, there is a, I mean, these leaks are also very interesting. If the leaks are small, there is a possibility that locally a clot is formed. Old patients will not have very high pressures inside the blood vessels. So therefore, there is a possibility that, the blood leaks, but it also clots and stays as a stable clot sometimes, and sometimes it may not be even detected. Not that all of us will have the same level of health condition throughout our lifetime. So we are referring to cases slightly different, not the case in every scenario. And we are also talking about this kind of coiling kind of a procedure. How many coils are required? They're also not a single coil. There will be several coils, one after another. They will keep on inserting. How many coils and what should be the packing density? These are all mechanical engineering kind of questions. So they want to know well in advance so that they're ready with those coils. And if they do craniotomy, by the way, meaning they open the skull, they'll put a clip, something like this. Okay, that comes under craniotomy. This is essentially a stent that you see here. This is what you see here is a flow diverter. Okay, so these are all the options that neurosurgeon does. And the clip that I'm referring, you can see the clip, and that's the kind of clip put in here. These clips are also, once they open the skull, they'll go there and just leave a clip like this. Initially, and of course they will cut it. Beyond this, they will just cut this beyond this clip, so that this clip stays permanently inside the brain. Okay, very it's going to be sort of, there are instances where please notice, when you put a clip should be having the right cinching force to be able to hold the blood vessel. At the same time, it should not be leaking. If it starts leaking, then it's counterproductive. At the same time, it should not shear it also. It should not shear like a scissor and then just release the whole thing. No, very dangerous. So clip designs are also, again, when you press, it opens. The scissors opens. Whereas in scissors, when you bring the two circles together, the scissors shears. Okay, these are the kind of coils that we are referring to in the zoomed view of this kind of a coil. And here we are talking about flow diverters. Again, the materials, biocompatibility issues, hemodynamics, and so on are critical. And then, of course, what kind of solutions to do and so on. I'm just showing you quickly. I think I'll skip this slide. This is about, I think I'll skip all the slides. I think, I'll skip all these slides because the whole discussion is about fluid structure interaction. If required, I'll come back to that. Yeah. Here we are talking about solving these equations. Something called mass momentum conservation equation along with the equation of structure. And I just want to know how much time, how are we doing on time? Another, how long can I take?
5 to 10 minutes, sir.
5 to 10 minutes. I'll try to close. I'm sorry. I think your listeners have been very patient. I think I'll straight away come to some important slides wherein, if we are doing fluid structure interaction, it's important to identify in CFD what is the, the blood flow domain, and then you essentially reconstruct from the CT angioradiological data and put together. This is all image analysis and processing. Once that is done, of course, you get into, you can see the the fluid mesh is essentially blue one. The wall mesh is essentially the black one. At the interface, you will have at the interface you will have interface bound. Can somebody switch off the microphone, please? So the velocity variation that you see here is essentially transcranial Doppler velocity measurement. It's measured using TCD, and then you can see very again as if the entire the vasculature, the blood outside whatever is the blood vasculature, and then the inside part is here shown. And then again, interface boundary conditions and put together is what I mean. CFD is all about that. And then here we are talking about CT angio, do the angiography, then get into the identification process. This is until this point the surgeons have to help you, or a neuroradiologist has to help you. Once it's identified and you separate out the vasculature, you identify what is the inlet tube, what is the outlet tube, and then what kind of hemodynamic activity you are interested. And then you do a mesh generation for that entire domain with the blood part as well as the outer containing wall structure part. Then you will do fluid structure interaction. Once you do that, you can use open foam, or again, these calculations are not exactly full-scale dynamic calculations. You can see how, as a function of time, these aneurysms would have evolved, and then some flow features are being shown, and under what conditions, let us say the balloon is gradually growing, under what conditions is it likely to rupture, if there is a small aneurysm, is it likely to be, safe aneurysm until next 1 year, 2 years? They're also very slowly growing ones. They're not like one day they will suddenly grow, and then the time scale at which you are seeing here from a very healthy artery now all the way to slowly growing is like several years. It's not like suddenly they grow in no time and then sort of become ruptured. Okay, even if they're growing slowly, we'll not even know. There won't be any symptoms until and unless it's pressing some nerves and then give you some symptoms. Okay, so it is like as simple as this. If your tube, which is supplying water to your pipeline, is slowly expanding, until it bursts, you will not even know, because which pipe, where, who is noticing? Nobody is noticing in the way there are millions of such tubes inside the body. Okay. Here we are talking about how to actually, the process of mesh generation itself is not that simple. You have a raw, 3D slicer model, and then, you use VMTK, and there is some smoothing process. Once you smooth, you also do the extrusion and end caps, and then only you think of a mesh. Here I'm talking about some validation mesh sensitivity studies kind of thing. I think I'll skip this. You can see in terms of morphology, there are tons of hemodynamic parameters related to, these are all wall shear stress based. Once you have pressure and velocity, based on velocity and gradients of velocity, one can construct what is called wall shear stresses. On the wall, how is the fluid shearing on the wall? If it is, with pulsatility effects, because the flow is not a steady flow. There is a pulsatile feature. You can see the pulsatile feature here. I specified this, this variation, right? This is the kind of real pulsatile feature that is obtained from transcranial Doppler. This is given as input to one of these tubes that you are seeing here. Okay, so under, you can see that this part is systole and this part is kind of diastole. During systole, there is a fluid acceleration and a deceleration, and during diastole, there is almost a kind of quiet phase. Okay, so if we do the CFD calculations, and then you are interested in really looking at, here I'm showing you a bypass. I think I'll skip this. What I perhaps want to talk is maybe last few minutes. Yeah, we may be interested in, for example, I think this will be an interesting example. Some of you may be, thinking that how mechanical engineers can help. Of course, this is done retrospective, by the way. This is not done as a suggestion to the surgeon. There was a giant aneurysm, big aneurysm was sitting. This is an ICA aneurysm, somewhere sitting in the middle cerebral artery. And the only option for the surgeon was to do a what is called a put a radial graft. and ligate this, completely close this, this is closed. You can see this black line is closed. And then facilitate blood supply from the external carotid all the way into this direction so that, blood supply is restored. Okay. This is more like what is called the fluid going into the upstream, more like a reverse flow. The radial graft is what is used. Okay, touching this is dangerous. After 3 months, you can see this big size aneurysm kind of thrombosed and became smaller in terms of flow domain. What you see is the flow domain here. Okay, it's a nice clot is sitting and nice endothelialization and so on. And surely it's a very successful bypass surgery. Not really a bypass; it's more like a radial graft, and then you can say bypass because you are completely ligating this, and you are trying to reduce the hemodynamic forces straight away onto the big aneurysm that you see. And we analyzed this extensively to prove why it is a very successful bypass. And those details, of course, I do not want to really get into the specifics, but then, the whole idea is look at this. The time averaged wall shear stresses, especially after the bypass was done, radial graft was done, you can see that, there is a lot more, you can see it's almost very cool. Okay. In terms of the wall shear stress activity, it's really, when the flow was passing through the internal carotid, it was at high velocity, and naturally there was very high wall shear stresses which were generated, and that activity reduced. Okay, and also of course there is a lot more fluid recirculating there locally, and that's what is measured through this index called relative residence time. And once the relative residence of the blood is much larger, a clot nicely forms, and then that's responsible for reduction of this size into something like this. You can see this. It is again, this is back to normal. Nothing is residing here. So relative residence time is much larger in this case, where we essentially did three, separate stages of hemodynamic surgery for the bypass: prior to surgery, soon after surgery, 3 months after surgery. 3 months after surgery, again CT scans were taken, and then that surgery was analyzed for its hemodynamic feature. I think I'll stop here. I just want to maybe I just want to take up some questions, and then the process also talk about some of the publicity activities. Yeah, publicity activity. Of course, this kind of work is naturally, he is the neurosurgeon. He works in Trivandrum. He is additional professor. He closely collaborates with our group. Of course, we are funded by National Supercomputing Mission. We are funded by American Express. We are also funded by Supra projects, and now we have ANRF thing also. And these are some of the stuff that rupture risk predictions is what was done, and some of the papers are also covered extensively in popular newspapers. Again, AIP has covered this story extensively in terms of cover story kind of a thing on there. Then again, one of our student who got again, he's a single mother child. A lot of stuff is written in Marathi, but of course he was with us for about 1.5 years. And this boy went for Mary Curie Fellowship. So Mary Curie Fellowship is a huge money. Figure out how much money you will get. So this is motivation for two reasons. One is, research also has good funding, good scholarships. And of course, one of my students is a CEO in this company, the Impella pump that he's, really designing. It's incubated, and of course, that credit doesn't go to me. He is the CEO not because of he is my student right now. But the key point is this flow aid company is actually trying to develop, Impella pump. For that Impella pump, originally I was showing, there are about 12 to 13 competitors in China, and there is only one company, this Fluid.com, attempting that, trying to sort of produce alternatives, because impeller pump costs about 20 lakhs. Surely some of my scholars from Andhra. This guy is a scientist. Dr. Sridhar Muddada is a scientist in NIOT. I'm just showing, not that many AP faculty are afraid to come to IITs, and then they want to locally get their PhDs. You can do it actually. There is nothing. I have studied in SRKR, and this boy also did BTech. He joined for masters, then converted to PhD. He's a big scientist now in NIOT in Chennai. And of course, IGCAR, he is a scientist, and his name is Sanapal Satyam. Again, he did BTech from JNTU and SG Markapuram. He did HBNI, of course, it's a school, and then PhD because he worked on liquid sloshing dynamics and fluid structure interaction, of course. Dr. Harish Pothukuchi is a faculty in IIT Jammu. He's also going to speak on one of these days. He worked on flow boiling extensively, and then he was also co-guided by our colleague Professor B.V. Triples Prasad. Of course, he is from your Godavari district. He was, because he passed away during COVID time. Again, Bolam Srinivas is from Vizag. He also studied in Rajam, and then I'm specifying this because some of the PhD scholars or MTech students sitting in this audience should not think that this boy worked on some of the rupture risk prediction. He's a BTech computer science, MTech computer science. He did PhD with me, and he worked on the computational modeling and analysis of patient-specific images, because image analysis is also part and parcel of this, and then therefore, it's quite fair. He's also with NIOT. He takes care of the complete computing systems in NIOT. So he worked on the high performance calculations and so on. I think. Thank you for your patience. I think I'll stop here.
Thank you, sir.
And then,
Thank you, sir. Now the forum is open for questionnaire from the participants. The participants can raise your doubts and question to our today's session speaker.
Yeah. Raman Janeluji, go ahead. Dr. Srinivasan. Yeah.
Sir.
Raman Janeluji, go ahead. If there are any chart questions, people
Sir, we have two questions in the chat box from Dr. R. Srinivasan.
Yeah.
How fatigue life of material is important?
Oh, quite serious. Because the one that I have covered is only hemodynamics related, and the fatigue life of of the valves of think of high cycle fatigue. Material fatigue is quite serious. That's the reason for older patients, tissue valves, I think there's a lot of. Please switch off the microphone if you are not speaking. Whoever it is, don't keep the microphone open. Yeah. So the fatigue life is quite serious because the tear of the valve, etc., is something not uncommon for tissue valves. So the bovine and porcine valves are prone to tear, and therefore for geriatric patients, old patients, they prefer a tissue valve, which is more biocompatible. Compared to mechanical valves for younger patients, they want that mechanical valve to last at least 20-30 years and so on, without any, they will be taking blood thinners throughout their lifetime. The viscosity, blood viscosity is reduced, and then, but that also has repercussions. Clotting issues are also going to come in and things like that. So they'll be on warfarins continuously during their entire lifetime. So the key issue is fatigue life is that's where the materials rules the whole story. The CFD part of the design is only making sure that the biocompatibility is automatically taken care. Nickel, titanium, etc. Again, there are many aspects associated with this. The suture ring will have one type of material, and then the valve will have another type of material. All that parts are kind of almost quite well known in terms of orthopedicians also know extensively on that. But here we are talking about interaction with the blood. Under blood interaction, you have additionally the problem of hemolysis, the lysis aspect of the red blood cells getting damaged under high shears, and the clotting issue. Once a clot is formed, a thrombus is formed, that is likely to cause serious additional difficulties. How to overcome these two are the major concerns. Here I see how a general mechanical pump will take care of. It's not a general mechanical pump. It's a specially designed. I mean, there are many design features which we have not talked about. It's not any mechanical pump. We are talking about several stages of the design that I have mentioned. So the viscosity changes in blood. There will be viscosity changes in blood due to blood thinning, but otherwise, if the pump is actually drawing blood, and simply the viscosity change happens because of RBC dominating the viscosity of the blood. If the hematocrit levels are larger, meaning the red blood cell fraction is very high, you go to high altitudes, live there for 6 months, your red blood cell fraction will shoot up. Because of low pressure, the red blood cell production will also get ramped up. Whereas somebody like me in Chennai going all the way to high altitudes and living there will find it very difficult initially for several weeks and maybe first few months. And then later on, of course, we'll get used to it. Because red blood cell production has gone up and the RBC fraction will be much larger if you are at high altitudes. Okay, because of low pressure, the oxygen carrying capacity of red blood cells will be reduced, and therefore the red blood cell body automatically produces large quantity of red blood cells. Of course, it is what is called homeostasis. The body will be in equilibrium with its surroundings. That surroundings is typically internal surroundings is what we are referring. We getting adjusted to external surroundings can happen quickly. If outside is very cold, I can switch on the heater. If outside is hot, I can switch on the air conditioner. But the body also has to come to both static and dynamic equilibrium with its internal environment. That's what is called homeostasis. Yeah, homeostasis is very critical, and then I mean, all doctors try to treat the individuals based on homeostasis. And yeah, what is the other question? I'm not able to find.
Sir, pardon, sir.
Yeah, mechanical engineers are scared of this kind of red blood cells, clotting and all that. Yeah.
Thank you, sir.
Yeah. Thank you.
Thank you, sir. Now I invite Professor Dr. Francis Luther King to give vote of thanks.
So thank you, sir. Today we had a very insightful and interesting session. On behalf of Management, Principal, Vice Principal and Department of Mechanical Engineering, Swarnandhra College of Engineering Technology, Narsapur, Andhra Pradesh, we extend our heartfelt gratitude and sincere thanks to our Day 1 Session 2 speaker, Dr. B.S.V. P. Patnaik, Professor, Department of Applied Mechanics and Biomedical Engineering, IIT Madras, Chennai, Tamil Nadu, who has shared his expertise in the knowledge sharing platform on the topic modeling and simulations in biomedical device designs. Today we had a very wonderful session, sir. We could learn new things like different heart walls, caged ball, monoleaflet, bileaflet, especially new terms like blood hemolysis, pump thrombosis, and similarly like cardiovascular devices and etc. So it was quite interesting and incredibly informative. We are grateful to you, sir, for accepting our invitation and much thankful for your representation for being a session speaker in this FDP. Thank you, sir, once again on behalf of the organizing committee and on my own behalf, I extend my sincere thanks to you, sir. Thank you.
Thank you. Thank you. I think many participants are there till the last minute. I'm grateful to all of you guys. Yeah, for showing your, what should I say, patience. It's a difficult area. It's not very traditional. Fluid mechanics itself could be boring, and any interface with biofluids is not easy because it has its own, stages. Only when you see the patient-specific scenarios, then you will realize, yeah, the story is more complicated than this. So it requires research, scholars who are willing to sort of really work in this kind of fields. Yeah, it
Thank
is
you,
not
sir.
like you will feel excited only when you see your product really doing well. Yeah.
Thank you very
Thank you,
much.
sir.
Thank you so much, sir. Your support. Welcome, sir.
Yeah. Thank you. Thanks a lot.
Thank you.
Bye bye.
Thank you, sir.
I
The
can leave,
feedback,
right?
the feedback and attendance link will be posted in the chat box. It will be active for the next 15 minutes.
Thank you. Thank you. I'm leaving.
Okay, sir. Thank you,
Yeah,
sir.
thank you, sir. Thank you.
Bye bye.
Thank you, sir. Thank you, sir. Okay, sir. Yes, sir.
Bye.
Last group photo is taken.
Tomorrow we will meet with new topic with other eminent resource person. Thank you all.